This is part 2 of a series on autoencoder. In this video, we will look at noise reduction using autoencoder models. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the previous video, we looked at dimensionality reduction using fully connected autoencoders and CNN-autoencoders. In this video, we will look at noise and blur removal using CNN-autoencoders and LSTM-autoencoders. First, let's look at the CNN-autoencoder model for denoising or deblurring. We generate a training dataset by intentionally adding noise or blur effect to the original images. These are the feature data X with added noise or blur effect, and these are the target Y, which are the original clear images. The images in this example are samples from the fashion-MNIST dataset. Configure the CNN-autoencoder model as shown in the figure. The encoder consists of 2D convolutional layers, and the decoder consists of 2D transposed convolutional layers. This is similar to the model we used for dimensionality reduction in the previous video. This time we will use this model to remove noise or blur. We feed these images to the model for training. The model uses them to learn how to reconstruct these clear images. The first input image is a noisy ankle boot. The first output image is a clear ankle boot without noise like this. Once training is complete, we feed this model some noisy or blurry test images. Then this model will output clear images like this. This test image is a shirt with added blur. If you input this image into this model, it will output a clear shirt image like this. Dimensionality reduction models only use the encoder during the prediction process, while noise reduction models use both the encoder and decoder. Next, let's write code to add some noise and blur to the fashion-MNIST images. Load the fashion-MNIST dataset. This dataset contains 60,000 pieces of training data and 10,000 pieces of test data. We will only use the training data. Of these, we will only use the image data X. Each image is 28 by 28 pixels in size, and each pixel is represented by a single value between 0 and 255. We normalize the pixel values to a range between 0 and 1. Add Gaussian random noise to image data X. Clip pixel values outside the range of 0 and 1. This will give us X noise, which is the image data with Gaussian noise added to X. Add a channel dimension so that the image can be fed into a 2D convolutional layer. Next, let's take a visual look at the noisy images and the original images. The results are as follows. The ones on top are the original images, and the ones on the bottom are the images with added noise. And save these images for later use. Next, we apply motion blur to the fashion-MNIST images. We used a circular averaging kernel of size 10 by 10 pixels, centered at 5,5. Here are some images with motion blur applied. And save these images for later use too. Now let's use a CNN-autoencoder model to remove the noise from the fashion-MNIST images. Read the dataset we saved in the previous code. Data X is a set of the fashion-MNIST images with noise added, and data Y is a set of the original clear images without noise. We feed the noisy images X into an autoencoder model and train the model so that the outputs Y hat are as similar as possible to the unnoisy images Y. Split this dataset into training data and test data. Build a CNN-autoencoder model. Create an input layer. The noisy fashion-MNIST images of size 28 by 28 by 1 are fed into the input layer. The 1 at the end is the number of channels. Fashion-MNIST images are grayscale, so there's only one color channel. Next, we add a 2D convolutional layer. The number of filters is 10, and the kernel size is 3 by 3. Set the stride to 1 and padding to same. This layer will then output 10 images of size 28 by 28. The 10 at the end is the number of filters. This is the output of the encoder. Next, we create a decoder. Add a 2D transposed convolutional layer as follows. This layer also outputs 10 images of size 28 by 28. The last 10 is also the number of filters. Finally, we add a 2D convolutional layer. Setting the number of filters to 1 will output images of size 28 by 28 by 1. This has the same dimensions as the input image. The activation function is set to sigmoid. This is because the MNIST images are normalized to values between 0 and 1. Create and compile a model. We use binary cross-entropy loss. Fit this model to the training data. X-train is a set of the fashion-MNIST images with noise added. And Y-train is a set of the original clear images without noise. During training, the training error and the test error are reduced like this. Now that the model has been trained, let's feed test data to the model. X-test is a set of fashion-MNIST images with added noise that were not used for training. The model's output, XPred, will be similar to the original clear images without any added noise. That is, XPred becomes a set of images from X-test with noise removed. Let's visualize X-test and XPred to see how much noise has been removed. The results are as follows. This is the image with noise added, and this is the image with the noise removed. And this is the original clear image. You can see that a lot of noise has been removed. Let's run this code. We got the following results. Next, let's deblur the fashion-MNIST images using a CNN-autoencoder model. Read the previously saved dataset. Data X is a set of blurred fashion-MNIST images, and data Y is a set of the original clear images. We feed the blurred images X into an autoencoder model and train the model so that the outputs Y hat are as similar as possible to the clear images Y. Split this dataset into training data and test data. Build a CNN-autoencoder model. This model is the same as the one used in the previous code. Let's just check the results. This is a blurred image, and this is a deblurred image. And this is the original clear image. You can see that a lot of blur has been removed. Let's run this code. The results are as follows. Next, let's remove noise from time series data using LSTM-autoencoder. The structure of a LSTM-autoencoder model is as follows. Both the encoder and decoder consist of LSTMs. We sequentially input the noise time series into the encoder LSTM. The output of the encoder is a latent vector of the input time series. This latent vector is duplicated as many times as the number of time steps and fed into each time step of the decoder. At each time step of the decoder, the latent vector and previous hidden states are used to reconstruct the denoised time series values. The LSTM in the decoder is a many-to-many model. This is because the reconstructed time series values are output at each time step of the decoder. Therefore, the output layer consists of a time-distributed dense layer. After training is complete, if you input a noisy time series to the encoder, the decoder will output a noise-free time series. Next, let's generate a time series with some noise. We set the number of time steps to 50. Generate 2 sine curves. And we add Gaussian random noise to each curve. Generate data for the encoder using a noisy time series, and generate data for the decoder using a noise-free time series. Finally, we visualize the data with and without noise. And we save them for later use. The results are as follows. This is the time series with noise, and this is the time series without noise. Let's run this code. The results are as follows. Now let's implement an LSTM-autoencoder model for noise removal. Read the dataset we saved in the previous code. Data X is a noisy time series, and data Y is a noise-free time series. Split this dataset into training data and test data. The number of time steps is 50, and the number of features is 2. We build a denoising LSTM-autoencoder model. We use LSTMs to construct the encoder and decoder. We use repeat vector layer to duplicate the encoder's output by the number of time steps, creating a 3D tensor. Feed the results to the decoder. And we use a time-distributed and dense layer to get the final outputs. Create and compile a model for training. Since this is a regression problem, we use the mean squared error loss. Fit this model to the training data. Once training is complete, we feed the test data containing noise to the model. Then we can get a time series with the noise removed. Finally, we visualize the time series with and without noise to verify that the noise has been removed. The results are as follows. You can see that the noise has been removed like this. And this time series became similar to the original time series. Let's run this code. We got the following results. So far, we have used autoencoders to remove noise from images and time series. In the next video, we'll look at sparse autoencoders.